Good evening and welcome to this 19th session of Astro Adda, a series of astronomy sessions, popular astronomy lectures, followed with a little bit of quantitative explorations on part of you participants. Organized by Nehru Planetarium, Nehru Memorial Museum and Library, and Public Outreach Committee, Astronomical Society of India. And we have with us our speaker and myself. We are both part of this the POEC. And we have with us Dr. Sarita Vig from the Indian Institute of Space Science and Technology. Um, Her area of interest are star formation and star clusters, evolution, and so on. And so today she has promised, we were just discussing before this, Sarita and I, she promised to give you some HR diagram projects to do. There are many students who were asking for it. I was telling her that. So onward to star clusters, those jewels in the sky. So I'll hand over to you, Sarita, and also I
Okay,
will put
thank you.
your presentation here. It's
Mhm.
there. We are able to
Okay,
see your presentation.
yeah.
So
Thank you,
please.
Ratna. And thank you for this invitation to Astro Adda. It's really a pleasure to be here. And good evening and hello, everybody. So, today I will be talking about star clusters, which are like jewel caskets in the sky. So, I'll begin with talking about stars. So, we all have heard about stars. We look at the stars in the night sky, but how do we define a star? So, what is a star? So, generally, by definition, any body that is bound by self gravity and radiates energy from internal energy source. And when we say internal energy source, mostly it is nuclear energy, that is nuclear fusion. So, the consequence of these two is that the star is spherical because gravitational force is a radial force. So star is a spherical body and it has an energy generation from the very center by nuclear fusion. By this definition, therefore, planets, asteroids, and comets, they do not satisfy one or more of these conditions. Either they do not generate energy by nuclear fusion, particularly hydrogen to helium fusion, or they do not have this spherical shape. So the star that is closest to us, that is our star, is the sun. And because it is very close to us, we can study it in great detail. And the next nearest star, I think all of you know this, is Proxima Centauri, and which is like 4.24 light years away from us. Now coming to Milky Way, our galaxy, there are nearly, it is estimated that there are nearly 100 to 400 billion stars. Now, this is a very interesting question. How do we know that there are 100 to 400 billion stars? So, this is, people don't usually sit and count, but they do statistical analysis and they measure some kind of stellar densities, and therefore they make some intelligent approximations and then come to this kind of numbers. So, now what is the composition of a star? What is a star made up of? Initially, when people had just begun looking at stars in great detail, in the beginning of 19th century, they were not very sure. So when they first came up, when they looked at the composition by using spectroscopy, they found hydrogen, for example, and helium, and they were very surprised because they did not anticipate so much hydrogen and helium in stars. They rather thought that there'll be a lot of iron, there'll be a lot of silicon, and so on. But now we all know after so many years that it is mostly, in fact, not only the stars, but all the universe is mostly hydrogen, which is about 71%, and around 27% is helium. And there's also the composition of stars. And there is a small fraction of heavier elements. So, what do you mean by heavier elements? Any element which is more heavier than hydrogen and helium. So, you can think of carbon, oxygen, silicon, and so on. So, these, in astronomy terminology, these heavier elements are also known as metals. So that's why very often you may hear about stars with a certain metallicity. That means how much heavier element fraction they have, that is generally termed as metallicity. So what about stars? Can we classify stars? If you look at the night sky, I'm sure you have, many of you at various points of time, you must have seen that some stars appear reddish in color and some are bluish in color. So how do astronomers classify stars? Astronomers classify star on the basis of surface temperature. That is, what is the temperature at the surface. But this surface temperature, mind you, is very different from the temperature in the very core where the nuclear fusion will be occurring. Okay, so the nuclear fusion that I talked about happens in the very core, at the very center, where the pressure and temperature are high enough for nuclear reactions to proceed. That produces quite some bit of energy, enormous amounts of energy, which is then transmitted throughout the surface, entire surface, and comes out from the outer layers. These outer layers is known as the photosphere, or which is also termed as the surface in some sense. So as it is, as the radiation, as the fusion is happening in the very interior, there the temperature is very high, but the temperature falls off slowly till the outer surface. So there's a gradient, there's a temperature gradient, and it falls off from the core to the surface. And on the surface we can measure the temperature of stars by various means. Okay, so once you measure this temperature, you can actually classify stars on the basis. This was how people decided to classify stars. So stars are therefore classified on the basis of surface temperature, and they are in general, stars are found to have a range of temperature from 3500 Kelvin on the surface to more than 60,000 Kelvin. And based on this, their colors also changes, because these can be the surface of stars can be approximated to black body. So if you have some a black body which is at high temperature, therefore it will, most of its energy will be at lower wavelengths, right? That is higher frequencies. So the higher temperature stars will appear more bluish in color as compared to the lower temperature star, which will appear reddish. So astronomers have decided to give certain terminology. They gave some alphabets to it, and these alphabets, if you arrange it in the order of temperature, then it is this. The most massive stars and the most high temperature stars are the O stars, and then you have the B stars, you have the A stars, and this also reflects the size in some sense of the stars which are burning hydrogen to helium in the core. So these stars, the most massive stars which have the highest surface temperature, are also the largest stars. Then you have the B stars, which are smaller in size and have a different temperature, lower temperature range than the O stars, and so on. And but if you see each of these categories, it is not that you will find on O stars all of same size. There's a continuous variation, right? So instead of giving here certain as you can see, certain temperature ranges we have defined, but all those temperature, instead of putting all the temperature range to one star, they decided to make subclasses of 0 to 9. So you will have, for example, in A, the range will be, the temperature range will give rise to subclasses A0, A1, A2, and so on till A9, where A0, for example, is the hottest and A9 will be the coolest, and so on. In other sense, what this means is that you can define some kind of continuous temperature range based on this classification OB. So O will have from O0 to O9, but we have not seen any O0. Mostly we see up till O3 or O4 stars. Then B, for example, the range goes from B0 to B9 and so on and so forth. Now, what are the characteristics of these kind of stars? So for example, before we go into that, why did I put a circle around G? Because Sun is a G-type star. The surface temperature of Sun is around 5800 Kelvin, and that comes under category G, and which appears yellowish. So now you know why it appears yellowish. That's because most of the energy is given off at a temperature range at which it appears yellow to us. So going further into this classification, this is basically a chart describing what I have already told you right now. That is, the O stars have a temperature range 28,000 to 50,000. As you can see, this is a pretty large range. So suppose you have a star, for example, which is at a temperature of 40,000 Kelvin, and a star which is at temperature of 30,000 Kelvin. Both of them are O type, but because you want to further subclassify them, we decided to give this subclassification O0, O1, O2, and so on till O9. And this is the B stars, whose surface temperature range is from 10,000 to 28,000 Kelvin. And I hope you are familiar with the terminology Kelvin, which is very similar to, at these high temperatures, it doesn't really matter very much, but between centigrade and Kelvin, there's a 273, there's a scaling of 273 degrees. And these are A-type stars with a temperature range 7,500 to 10,000 Kelvin, and so on. As you can see, these are the coolest stars. The M stars are the coolest stars, and these have temperature range 2,500 to 3,500. Now, how do we know the temperature? One way that we know its temperature is by spectroscopy, and we look at the absorption lines in these stars. And O-type stars, for example, show typically ionized helium lines because these are the higher temperatures. And in fact, physics allows us to calculate that if the temperature is, for example, 30,000 Kelvin, and if you know the composition, what are the kind of lines you will see and what is the intensity of lines you will see and so on. So with physics, we astronomers are able to do these calculations, and therefore if and find out what lines you will see and what are the intensities. So therefore, once you have the spectrum of a star, you look at the absorption lines, identify them, look at their intensities, and then gauge the temperature by looking at the sequence of absorption lines and their intensities. The B-type star, for example, shows helium and some hydrogen. If you look at A-type stars, these show strong hydrogen lines. All of you, I'm sure, are familiar with the hydrogen spectrum, right? The Lyman series, Balmer series, and so on. So these are the lines which are seen in these kind of stars. It's strongest in A, because at these temperatures, the temperatures of this hydrogen absorption is seen to the maximum amount. One can do calculations and show. And why we don't see hydrogen in these other stars? Because in these stars, the hydrogen will mostly start getting ionized. So it will no longer be the neutral form. And if you go to cooler ones, then hydrogen is associated with other joints with other atoms and form molecules and so on. Okay. And there, for example, it is more easier to see other heavier elements, metals and ionized metals. So as I told you, metals are all heavier elements, all elements heavier than hydrogen and helium. And at this, for the K-type stars, you will only see these heavy element lines, and M-type stars, you see these kind of lines. Now, there are two important observables of a star. As I said, one of them is the surface temperature, and we do spectroscopy to observe them. And there's another way that if you measure the entire spectrum from, let us say, from ultraviolet, and you go on to infrared and so on, at least what you will find that this can be fit by a black body, and from the fitting you can find out where the peak is, and then you can use the black body laws to determine the surface temperature. For example, Wien's law. This is another way to determine the temperature. The other quantity that is of importance is the flux that is coming from the star. So the flux that is coming, that means the energy that we receive. But the energy that we receive from the star depends on the distance to the star. So if a star is closer to us, for example, you will get more energy. It's like you put two light bulbs at two different distances, right? Although they may be, for example, you take two light bulbs of same wattage, and you keep one close, keep the other very far. The one that is closer, you will receive more energy, right? Because it's closer. But the other one, you will receive less energy. The same is the case with stars. So in stars also we measure, but you need so if you want to know the, for example, in this case, suppose I measure suppose you come back to the example of two light bulbs, and I want to know what is the wattage of the light bulb. Then, for example, I should know how much energy I am receiving at my position, and I should know the distance to the light bulb. Once I know these two factors, I can determine what is the wattage, how much is the energy being released by the light bulb. Same is the case with stars. So the total energy released by the star per unit time is a quantity known as luminosity. But what we measure is the brightness. So that is shown. So the relation between the brightness, distance, and luminosity is given by this expression here. L is equal to 4 pi d square B, where B is the brightness that we measure in watts per meter square, and d is the distance to the star. So once you know the distance to the star and you measure the light being received from the star, you can calculate its luminosity. Now, this luminosity, can I relate luminosity to effective temperature? It so happens that since it is a black body, a star is a very close approximation to a black body, I can use another interesting relation which relates the surface temperature with the luminosity. So, according to Stephen Boltzmann law, which is a law in physics for black bodies, the amount of energy radiated by any black body depends on its temperature. So, the energy released per unit area is given by sigma T power 4. But the star has a certain area, right? That depends on the size. So, if R is the radius, then the area of the sphere is 4 pi r square. So, this is the energy released by black body. This is the surface effective temperature. This is energy released per unit area multiplied with the area, surface area, that gives me the total luminosity. So in this way, if you know the effective temperature and you know the radius, then also you can calculate the luminosity. On the contrary, if you know the luminosity and if you can calculate the effective and if you can measure the effective temperature, then you can also calculate the radius of the star. These are thus luminosity and effective temperature are two very important observables for a star. Okay, so people also related the different categories, like here you see, this is actually observations where they found, where they computed the luminosity and plotted it as a function of the spectral type or the solar mass. But before that, I want to add something else here. The luminosity usually is in watts, that is energy per unit time, but very often astronomers use a term called absolute magnitude. So absolute magnitude is related to the negative logarithm of luminosity. So sometimes when I show plots of luminosity, instead of luminosity, you will see absolute magnitude plotted there. And that's why I have brought in this term, just to tell you that it can be considered, absolute magnitude can be considered as a proxy to luminosity. So here, for example, as I showed you, the O-type stars and B-type stars are also the most massive, and their luminosity is very high. They have the highest luminosities. And if you go from O, B, A, F, G, K, M, basically you are going from very high mass stars to the low mass stars. You are going from higher effective temperature to lower effective temperatures. And also the luminosity wise, you are going from higher luminosity to lower luminosity. Now I want to introduce something called the Hertzsprung-Russell diagram, and this is a plot which relates the two observables that I talked about just now, that is the luminosity and the effective temperature. So there is an interesting history behind it. There were these two astronomers who almost simultaneously came up with this idea, because this was done at a time, this diagram was done at a time when people did not know a lot about stars. So what they did, they said, let us try to plot these two and see where stars lie in this diagram. So Adda, Hertzsprung, and Norris Russell, they made this diagram independently in two different places, I think in US and Denmark. And they published also independently. And later, astronomers found that this is an extremely useful plot to find out the properties of the star and to find out in their evolution, how they evolve. That you can see from this, because when they initially plotted, my guess is they would have thought that this will be kind of filled. You will find stars of all possible luminosities and you will find stars of all possible temperatures, and therefore this whole plot should have been kind of filled. But what they found was something very interesting. But before I go to show you what they found, I want to tell you a little bit about the scale. So on the y-axis in the HR diagram, this is also known as Hertzsprung-Russell diagram or the HR diagram. On the y-axis, you have low luminosity to higher luminosity going upwards, and the effective temperature increases towards the left. This is contrary to what we usually plot, right? We usually plot increasing quantities towards the right. But in this diagram, please note the temperature, effective temperature increases towards the left on the x-axis. So effective temperature is the surface temperature. So when they plotted stars in here, they found most of the stars were lying on a diagonal band like this, and they were like kind of surprised. So they knew this has to do with somehow with the properties of the stars, because why should it be that most stars are lying on this band? And later with physics, people are able to show that these two are related. And now you also know that they are related, but it's also related to how the energy is being transferred, what is the size of the star, and so on and so forth. So the lower temperature, this, as you can see here, these stars correspond to low luminosity and low effective temperature, which means these are the M-type stars, the lower end stars. And as you go here, this is a band, this is known as the main sequence band. Main sequence band correspond to the stars. I'm going a bit ahead and telling you what we understand about this. These are those stars which are burning hydrogen to helium in their core. What you understand about the star. Those kind of stars are main sequence stars. The sun is a main sequence star. So the main sequence stars lie in a band like this, diagonal band, where towards the right bottom, you have the fainter stars, the M-type stars, K-type stars, and so on. And then you have the G-type stars, K-type stars, and so on. And towards the top left, you have the O-type stars. Okay, so these O-type stars are also the most brightest, most luminous, and have the highest effective temperature, as we have already discussed. they also found some groups, isolated groups of stars. And as you know, luminosity and effective temperature are related by something known, are related along with the quantity called radius. So therefore, these ones, although they have low effective temperature, but they have high luminosity. So that means their radius would be larger. So that's why these were termed giants. Then even higher, there was this group of stars, they are called supergiants. And then there are these group of stars which have high effective temperature, but they have low luminosity. So these are called white dwarf stars. And as we will see, these are all related to the evolution of stars, how stars evolve with time. So in this plot, where does sun lie? So as I said, the sun has one solar luminosity, because as you can see, this is unit is solar luminosity. So it has one solar luminosity and effective temperature of roughly 5800 Kelvin. So that would be somewhere here. So this is where our sun would lie in this diagram. Now let us look at the life of a star. For example, I've just told you, right, that a star has so much luminosity, so much effective temperature, and there is burning of hydrogen to helium in the core. But how does a star come about? How is a star born? So people have studied the stars and looked at different parts of the sky, and they have come up with a sequence that helps us understand. This is of course based on the work of numerous and a very large number of astronomy researchers, and they have actually come up with the idea that stars are born from something called as interstellar medium. So if you see this picture, this must be very familiar to you, right? This is the Orion constellation, right? And in this, so now if I ask you, what do you see in this picture? You'll see mostly there are stars. But then you're also seeing some faded kind of diffuse thing which is here, and then there's something which doesn't look like a star, some blotch here. So what is that? So it so happens that between the stars, the region is not empty. It is actually made up of very, very rare medium, which is known as interstellar medium. So this very rare medium is how rare? It is more rarer than the best vacuum that we achieve on Earth. Okay, that is the number of particles per unit volume is very, very low. Okay. So again, that is known as interstellar medium. People classify interstellar medium into different phases depending on the density that is present. So for example, 10 power 5 particles per centimeter cube is considered very dense interstellar medium. But compared to the vacuum that you achieve on Earth, it is nothing. So this picture, which is the background picture, should tell you that there is this interstellar medium, because you can see a lot of stars here. Plus you see that there is lot of matter which is here, which you can see, which because of light being scattered from these stars. So this is the interstellar medium. But what is this interstellar medium made up of? What is it? Is it just gas? It is mostly gas, but there is also a small fraction of small tiny particles which is known as interstellar dust. So this interstellar dust, what is it made up of? It is mostly silicates, and it has other some, if it is cold in that region, it will also have some ices on top, and it will also have some amount of iron, some magnesium, some phosphorus, and so on. But these are much, much smaller than what you will get, or for example on Earth, if you say dust, you expect some micron or 10 micron size. So these the dust in the interstellar medium, people have modeled and have tried to find that this dust particles have to be very small, submicron sized, that is smaller than a micron. Okay, up till around not even 1 micron, up till around 0.5 micron is what they anticipate general dust to be. But in some region, they expect even larger sized dust grains in special conditions. Now, the next thing is, why do you need to study interstellar medium? Okay, so now let's get back to the story. How did we come to interstellar medium? Because we wanted to know how stars form. So first and foremost is why the reason we study interstellar medium is this is the medium from which stars form. But this is not the only reason that people study interstellar medium. The reason people also study is this is also the medium into which stars during various stages of its lifetime can eject matter. It can give off matter, like even sun. right? Sun is also giving off a lot of matter in the form of solar winds, right? So this matter, which is, you will think that's very little. Yes, it's very little, but where does it go? It will go into the interstellar medium. So this is the medium into which stars eject matter, and some violent events like supernova and so on, they give a huge amount of matter into the interstellar medium, and very processed matter. That means they will process it by fusion to heavier and heavier metals or elements, and they will be thrown into the stellar medium, interstellar medium. And therefore, over time, interstellar medium will slowly get enriched in heavier and heavier elements because of the processing happening in the interior of stars, which is thrown out into the interstellar medium. Okay, now coming back, what is the third reason? All bodies, planets, everything is made from interstellar medium. Now you may wonder where Earth is made up of interstellar medium, because it is formed from matter which um, it is formed from matter from which the star, the sun, and other planets formed. So it is all from interstellar medium. We are also from that, right? If we have come from the material here, and all this material, if you actually go back and say, where did the for example, titanium in earth come from, where did the silicon, we have a lot of silicon around, right? And we also have all this technological advances uses a lot of silicon, right? But where did this silicon essentially come from? If you go into the very basics, then you will see it has to come from the interstellar medium, because we are not building silicon within earth, isn't it? So all the things that we see around us have essentially come from interstellar medium. It has got processed in various forms, but the elements are from the interstellar medium. Now coming back to how stars form, our first point, this usually there is very dense interstellar medium like a dark clouds, and within that you'll have higher density small regions which are known as clumps. Within that you will have again high density regions which is known as core. So at some point of time, these clumps and cores, they start undergoing gravitational collapse. This can be because of triggering by some means, and the compression. It is a cloud which is kind of initially quasi-stable, but just some compression causes it to start collapsing. So as this collapse at the center, it's not that immediately you will start having nuclear fusion. It passes through various phases, and this is what is listed here. This is how the star formation phases, as star forming researchers envisage that you have this gravitational collapse happening. Then at the very center, this cloud also has some bit of rotation. Now as it is collapsing, what will happen? The rotation is going to increase, but matter is still falling. So because of that, most of the matter now is being pushed in the center through something called a disk. So this is the disk, this is the envelope, and matter is going into the star. So this is the rotation axis. And along the rotation axis, because the angular momentum becomes very high, some matter, it is found in nature that some matter is thrown off in direction along the rotation axis during the process of rotation. Okay, this is known as a jet. So these jets are given out, a disk is formed, and this over time at the center a star is formed which has a debris disk around it, and some matter around it may be present like this. Okay, and this disk represents the region. It is thought that this disk is the region from which planets are made. Okay, so most of the planets, over time this material forms planets, and the rest of the material slowly kind of dissipates, and what you are left behind are planetary systems. So you have a star at the center and you have planets moving around it. Now, what about massive stars? So as I told you, stars are of various kinds, right? You have O, B, A, very high mass stars to very low mass stars. The K and M type stars are low mass stars, and the O type stars are massive stars. So now there was this interesting question that do all stars form in equal amounts? Do you find massive stars also same number of massive stars forming versus the low mass stars forming? So when they if you just look at, take a survey of the sky and try to envisage properties, you find that massive stars are rare. If you see the main sequence stars, they are generally rare. But then the question came, are they generally rare, or they were produced in equal numbers, and over time the massive stars maybe because of some reasons evolved faster? So people wanted to study what is the fraction of different mass stars that are formed in the interstellar medium. So if you have a cloud like this and many stars are being formed, which is a fact, stars do not form in isolation. Usually they form in groups. Okay, they are called clusters. Okay, so these groups of stars, are all the mass stars present in equal amounts, or is there some kind of distribution that nature prefers? And it so happens that is known as the initial mass function. So this is, on the y-axis is the fraction of number of stars as a function of mass. So here you have the mass bin, and here you have the number of stars. You can just think of it that way. This is known as the initial mass function. And from this, what do you make out? You make out, these are of course different laws that people have used to fit, but you can take this as the trend which is seen in most clusters. People have gone and observed, and they find that low mass stars are very, what do you say, are abundant, are very abundant. They're found in large quantities. And as you go towards the massive star side, the number of massive stars being found, for example, 100 solar mass star, is probability is very low. Okay, so massive stars are not only rare, they are also born rare. And then, because this is an observable that people have found from studies, now people are trying to understand, using this, how to understand the process of star formation. Why should low mass stars be more, and why should high mass star be less? And why is this related to the dark clouds and clumps which are there, that these fragments, the number of low mass fragments are much more than high mass fragments? So people are doing analysis of this and trying to understand this process and the origin of this initial mass function. Now, after the stars are born, so when I say star is born, what does it mean? It means that it has moved to the main sequence phase, that is, it has started burning hydrogen to helium in its core by nuclear fusion. When I say burning, it is because of nuclear fusion. This is a terminology which we commonly use, but it's not the normal burning that we talk about in daily life. So this is the phase in which hydrogen is fuses to helium in the core, and this releases quite some bit of energy. This is the longest stage in the life of a star. Okay, and during this stage, the size doesn't change much, neither does the luminosity change much during the main sequence phase. It changes by a small amount, but not too much. Now, the sun, for example, is a main sequence star. And if you are curious, what is its lifetime, how long it will stay in this phase? Its lifetime, based on elementary calculations, is found to be 10 billion years. And where are we in that 10 billion years? Are we in the very beginning, or are we at the very end? It so happens that when we do radioactive dating of rock samples, or even analyze the meteor samples and so on, even meet some special old rocks from moon, we find that the age is around 4.6 or 4.56 billion years. Very accurate estimates people are trying to derive. So this is the age of the solar system. Now you may wonder, why do we need to go and look at meteorites? Why can't you use rocks from Earth? You can't use rocks from Earth because there's continuous geological activity and processing that's happening. And because of that, you will not find that they are very old, because they have continuously changed. So rather, you would like to look at very old fossils, or things which are not expected to change much. For example, asteroids, meteorites, and so on. So what are the properties of the main sequence stars? As I said, the more mass means it is brighter, but it also has more pressure and temperature in its core, and therefore the fusion is faster, and consequently the main sequence stars, the O and B stars, have much shorter main sequence lifetime than the low mass stars. The low mass stars have less mass, they have lower pressure and temperature in the core, and the fusion is also slower. So they are much longer life. So for example, if sun is 10 billion years, that's pretty long. But on the other hand, if you go and look at an O-type star, its lifetime would be like 100,000 years, which is much lower. So the more material that a star has, it also tends to burn it or fuse it more vigorously. And therefore, its main sequence lifespan also gets reduced. So this, for example, shows the different phases of the star. In O-type star, which is like 60 solar masses, 60 times the mass of the sun, nuclear fusion is happening only at the very core. But here, for example, if you consider M-type star, which is around which has 1/10 the mass of the sun, then there is nuclear fusion happening in a larger region, and it happens very slowly. The temperature, pressures is low enough. And these are also the zones by which energy, zones that represent the ways and means by which energy is being transferred. So the red represents the energy transferred by radiation. That means through radiation, energy is getting transferred. And this yellow represents the region through which energy transfer happens because of convection. That means matter is physically, heated matter goes up and cold matter falls down. So that is the way by which energy transfer happens. Now, what happens after the main sequence phase? After the main sequence phase, the stars can evolve differently according to mass. So, for example, if you have a very low mass star, I mean, if you have a star whose mass is less than the very low mass limit of hydrogen burning, then it doesn't form a star. It forms something called as brown dwarf. There is some nuclear fusion happening, some deuterium fusion, and so on, but it doesn't burn hydrogen to helium, so we don't call it a star in the normal sense. Now, if you consider stars that are burning, that are fusing hydrogen to helium in the core, then its evolution depends upon its mass. So I will broadly classify them into high mass, low mass, but in reality, it is a continuous range, and the processes through which it passes through are also slightly different. So, but more or less kind of between these two. So these are some kind of two extremes you can think. In low mass stars, which means in stars which are less than 8 to 10 times the mass of the sun, this is how they evolve. So sun is also expected to evolve in this way. So from the cloud, the stars are formed. So the low mass stars, they do not evolve much. They will remain, these brown dwarfs will not evolve much. They will remain more or less as it is. Whereas low mass stars, after they have finished fusing hydrogen to helium in the core, then it will become much larger in size, and its surface temperature will reduce effectively, because of which it will appear red. These are known as giant stars. So at some point of time, the sun will become a red giant star. And again, the last phase of this is the white dwarf. That is the core which is left at the center. This is not undergoing any nuclear fusion, but it will just be like a hot ball of matter, and over time this will cool and become dark. Now, if you consider a high mass star, that means a star whose mass is 8 to 10 times larger than the mass of the sun, then this is expected to become a super giant, a much larger giant. Okay, that's a super giant. And then at the later stages, at the final stages, it is the outer layers are expected to be thrown out in a violent explosion known as a supernova. And what will remain of the core at the center is that either it will become a neutron star, or it is expected to become a black hole. This is how the evolution of a star is expected. Now, I'm just talking about stars in general. I will move on to clusters soon. But all this has bearing on our understanding. So that's the reason I'm just talking about the basics in the beginning. So can we understand the evolution of stars that I just talked about in terms of an HR diagram? So people have done these calculations. They have done very elaborate calculations using computers, and they find that if you are taking a star like the sun, then it is expected to evolve through a giant phase, and it passes through this transient planetary nebula phase, and then it will become a white dwarf. So as long as the sun is a main sequence, it will remain here in this position in the HR diagram, because its luminosity and effective temperature are not expected to change in the main sequence phase. But once the main sequence phase is over, then things are going to change. Its surface temperature is going to change, its luminosity is going to change. Luminosity is going to increase, and surface temperature is going to decrease. And that's how it is going to be, and it's becoming much larger in size. So it's going to become a giant. Okay, it is expected, as it is passing through those various phases, as the temperature, luminosity is changing, you will see that it tracks this kind of path over, of course, many millions of years. But 10 billion years, it will be sitting on this point. Once those 10 billion years are up, it will actually start moving slowly over a few tens or hundreds of millions of years. And finally, it will settle down to this point. So this is the path it is expected to take. People have also calculated how the other stars are expected to evolve, and they are not identical. It depends on the mass and how the energy is transferred to the surface. What is the temperature, pressure in the interior, what is it outside, and all these factors go in our understanding of the evolution of stars beyond the main sequence phase. So this just gives us some parameters, of course, of the main sequence stars. This already you know. This is the main stellar groups in the HR diagram were what? the main sequence stars, the giants, the supergiants, and the white dwarfs. So just to give you an idea of the parameters, so the main sequence stars have surface temperatures, as you know, which are this. These are the radius. As you can see, the cooler stars have much smaller radius. This is the mass in terms of the mass of the sun. This is the luminosity, and this is the lifetime. So as you can see, O-type stars live only 10 million years. But if you take G-type star, which is the sun, is 10 billion years. Okay, and this is K and M-type stars are expected to live for 2 into 10 power, let us say 11 years. Isn't it? Very long lifetime. And then this is the group of giant stars. They are low mass stars near the end of their lives, as we have seen. And their spectral types are these. They are cooler and so on. These are white dwarf stars. They are dying remnants, right, of the low mass stars. And this is their very high surface temperatures. Okay, and they are very small in size. Supergiant stars are high mass stars near the end of their lives. Their temperatures are also 4,000 to 40,000. That means they can get really hot. You can have a blue supergiant also. And their luminosity is very high. Okay. So these are the various groups. And now you know how to relate these groups, right? For example, giant stars are the evolution of these low mass stars will become giants and then become white dwarf. Whereas the high mass stars are expected to become supergiants and then become neutron star or black hole. These are, of course, very broad phases. In reality, people track out, astronomers track out in detail what are the various phases through which a star passes through before it reaches its final stage. Now, this is about stars and their how they evolve, their properties, and so on. Now, what is a star cluster? How do you define a star cluster? So, as I said, a star cluster is formed from the same molecular cloud. That molecular cloud is this dense cloud of interstellar medium that is generally termed molecular cloud because in this medium, the temperature is so low that hydrogen is in molecular form. That's why it's called a molecular cloud. So in this molecular cloud, as you know, you'll have clumps, cores, and so on. And from there, you get stars forming through the manner described. And therefore, from a molecular cloud, you'll have a cluster of stars forming. Usually now, initially people were wondering, can you form a single star from one cloud? But now we know for almost with certainty that you cannot form stars with isolation. There is always some process by which there is fragmentation of the molecular cloud leading to the formation of a cluster of stars. So a cluster of stars is a group of stars which is formed from the same molecular cloud at around the same time. When you say around the same time, there may be few hundreds or 100,000 year difference and so on. In the overall time scale, this does not matter much. So we say almost formed at the same time. These are mostly gravitationally bound, either strongly or they can be loosely bound with the molecular cloud also. So a cluster of stars, but if you want a general definition, this is not a general definition, is a cluster of stars is a high density group of stars. Okay, aggregate of stars which has higher density than other surrounding background density of stars. Okay, and they can be gravitationally bound. They will have the same amount of metals. Their composition will be more or less the same. They formed at around more or less the same time. So this is what a star cluster is. So what are all the star clusters same type? As we see in nature, people have broadly classified clusters into two types. What I have been talking about, that is known as open clusters, formed from molecular cloud by the process of fragmentation and so on. They are open clusters. So one open cluster is shown here. This is NGC 3608. And this has open clusters have hundreds to thousands of stars. These are rich in heavier elements, which is metals. And these stars are found in the disk of the Milky Way. They are found to be, of course, very young because their age is a few million years to few giga years. And they are associated with the remnant gas and dust. On the other hand, globular clusters is thousands to millions of stars. They are generally spherical in shape and they have a wide range in metallicity. They are found mostly above and below the disk of the Milky Way, and they are very old, almost some of the oldest objects in the universe actually, and in the galaxies also. The age is of the order of tens of giga years. So near the center of the Milky Way also there are some special clusters. Now these are special clusters because they are found to be very luminous and very high density clusters. Okay, so two clusters for example are shown here. One is the Arches cluster and the other is quintuplet cluster. So people also study clusters because these are found near the centers of galaxies which are very active regions because of the presence. Sometimes there may be a supermassive black hole that is present near the center that can, and there's a lot of activity going on there. So the clusters formed there are also found in kind of different conditions, and therefore people study them with a special interest. Then there is a third type of cluster, which is a superstar clusters. These are massive young open clusters. Now, these are clusters which are found in some regions, not in Milky Way, but this is an example in the Large Magellanic Cloud, a satellite galaxy of Milky Way. And this is in 30 Doradus region. This is found to be probably, we believe that this is the most luminous and most massive cluster because, as I told you, high mass stars are expected to be rare. But in this cluster, there are hundreds of 100 solar mass stars. In fact, even in our galaxy, to find 100 solar mass star, it's very difficult. Maybe you may find in Arches and cluster and so on, but normally 100 solar mass star is very difficult to find. But in superstar clusters, these are found in large amounts, nearly hundreds of stars. But in this one, for example, there are hundreds of stars which are present. And now, how are these very rich and very luminous clusters formed? These are believed to be formed between the interaction, due to interaction between galaxies themselves. This is one of the hypotheses. So because of the interaction of LMC with, for example, the Milky Way, these kind of clusters may have been formed. Now, as I told you, as a star evolves, so for example, the sun evolves off the main sequence. So if this is the cluster, we know in the beginning that you have in a cluster, you have stars, a main sequence band passing from O-type stars to M-type stars. So as I told you, the O-type stars evolve the first and they will move off the main sequence because they evolve very fast. So at certain time, you can know the age of the cluster by looking at the turning point of the main sequence band. For example, in this figure here, all these massive stars have evolved off. They have now evolved off to higher mass, other evolutionary phases, maybe supergiants, maybe red giants, and so on. And this is now evolving off. So if you know the age, because this is at the turning point when it is just moving off, that means its lifetime. For example, and if this is one solar mass, that means at 10 billion years, it will be just beginning to move off. So from that, you can estimate that this cluster is 10 billion years old because at 10 billion years, these stars have evolved off and sun is just moving off. Sun is, of course, now not a part of any cluster, but I'm just giving an example. Okay, because most of the stars probably from its sun formed, they have all kind of got dissipated into other regions. Okay, coming back. So one can find out ages of clusters by looking at this something called as the turn-off point, because this is the point over which the star moves off the main sequence band. And this is a small kind of animation which shows this, which is the evolution of a cluster with time. So let us go back, for example. So at 10 million years, this star is evolved off. At 100 million years, this is how the cluster is evolving. At 1 giga year, so by looking at the star in the turn-off point and looking at its temperature, and you know how much time it will take to evolve off, and therefore you will get the age of the cluster. So the age of the cluster is generally determined by this turn-off point in the HR diagram. And this is HR diagram of open clusters, lot of open clusters taken with Gaia. So different colors kind of represent different clusters. So here you can see, for example, the blue ones are very young clusters, right? Because you have a lot of, don't worry too much about what is on the x-axis, but this is essentially in some sense kind of temperature, and this is kind of the luminosity. So here you have, for example, the higher mass stars which are still in the main sequence phase. So they are still burning. But on the other hand, if you look at the red ones are those which are moving off. So for these, this is a plot of many open clusters. So the red, each color represents one open cluster. So you have many points of a single color. So therefore, the maroon points are older because the stars which are heavier than this turn-off point have evolved off. And this is younger than this cluster, and this is younger than this cluster, so on. And the blue ones, for example, are the youngest clusters. That is also seen from the HR diagram of globular clusters, because these are the oldest clusters. They have a large number of stars, so we can create very elaborate HR diagram. So by looking at this, this is the main sequence band. By looking at this turn-off point, you can in fact, because it has large number of stars, hundreds, thousands to millions, you can actually see the different branches like the red giant branch and so on. Different evolutionary phases of the star you can sample by studying this HR diagram. This, for example, is, as I told you, two clusters are shown here. And from this, you can immediately gauge, right, which is the older cluster. The older cluster is, of course, the blue one, NGC 188, because at the turn-off point, it has lower effective temperature, and therefore those lower mass stars are just at turning point. All the higher mass ones have evolved off. On the other hand, the M61 compared to NGC 188 is younger. And this is a comparison of the different kind of clusters, the HR diagram, as I told you. This is the open clusters, and they have just shown, instead of points, which may be confusing, this is a schematic where they have drawn lines to show the path. A number of open clusters are shown here, right? And you can immediately see that these are very young, because the turn-off point is is pretty massive. Okay, and among these, this will be the youngest cluster, and the oldest one is M67. On the other hand, if you look at globular clusters have a large, they are very old. So most of the stars would have evolved off, so that they will be really much lower. The turn-off point will always be much lower, and you can, because they have a large number of stars, you can sample the different branches. So these are the different branches of the globular cluster. This is the main sequence band. This is the turn-off point. This is when hydrogen, this is the red giant phase, when hydrogen, at the center there's no fusion, but hydrogen is burning in a shell. Then at the center, helium begins to burn, and that is known as the helium flash. Then you have in the center, helium and hydrogen burning, that's known as the horizontal branch. So people have not only made models to understand these various processes in the interior of stars, but with the help of clusters, we can actually sample out these different evolutionary stages, how stars evolve with time. So now I will talk briefly, maybe in a couple of minutes, of the kind of clusters I am interested in doing, studying. And I have been studying, for example, both embedded clusters as well as globular clusters. So embedded cluster, as I told you, are some of the clusters in the earliest stages of the star formation, when the cores have collapsed and you're just seeing this cluster. The stars have just formed and they're still embedded in the molecular cloud. That means they're enveloped in clouds of gas and dust. Because there's a lot of gas and dust, you may not be able to see them in optical light, because the light gets absorbed by the cloud. So usually we see these clusters in infrared. So infrared is a good wavelength band in which to study them. So as I said, you have this small clumps, cores, and then they form a cluster of stars. And we study this young embedded clusters. So I'll just show you examples of some clusters that we have studied with our group. For example, this is one cluster where you can see, in these clusters, you will see a lot of associated gas and dust and so on. This is one cluster. This is another cluster. And this is an infrared wavelength, okay, all of you. In optical, if you look in this region, you will not see anything. You will just see stars, because the light is completely absorbed by the gas. So you will not see this cluster of stars, what you see here. Okay. Then we have also looked at, for example, one globular cluster, and this was using the AstroSat on using, all of you I hope are familiar with AstroSat, right? And we used the ultraviolet imaging telescope to image this particular globular cluster, which is NGC 2808. And we found some things very interesting. For the first time, we found a new population of new population of ultraviolet stars. They're not really very hot, but this was a new population of stars which are not seen earlier. And we have kind of found this new population that means it's different from the other kind. And we have been able to segregate this based on some kind of color magnitude diagrams, which are kind of like HR diagrams, not exactly, but very close to HR diagrams. So with this, I kind of come to the end of the presentation about star clusters. And this was the star activity that I thought some of you may be interested in doing. in making HR diagrams. So would you be interested in making HR diagrams? So if you are, then this is one of the simple ways to go. So if you want to make HR diagrams, what are the two parameters that you need for a star? The two parameters that you need are luminosity and effective temperature. So suppose you take a number of stars and you are able to get its effective temperature and luminosity, then you should be able to plot it, right? And then see whether the stars, whether they indeed fall in the groups like what I have shown you. So this is what the HR diagram you can make using some not too many resources. See, as astronomers, what we usually do is we measure the brightness of stars, we do a lot of data analysis and so on. But since many of you would like to do it more like an activity, so if you know the luminosity and effective temperature of stars, you should be able to make this. So thankfully there is this very nice software called Stellarium, which gives us a lot of information about stars. Anyway, so if you want to do this, all you need is a computer or a laptop, and of course pencil, paper or notebook, and a graph paper. So as I said, you need the software Stellarium, and most of you may have it already, but if you don't have it, then you can install it. This is of course a free open source software, and it's like a planetarium. And
Would you like me to screen share and show Stellarium? Though perhaps
maybe at
some
the
of the
end I
information.
can, maybe in 2 minutes I'll
Yes,
finish
yes,
and then you can show. I have one screenshot of Stellarium. After that, you can show. Actually, it will be good if
yes,
you can show. So
yes,
I'll
yes.
just show a screenshot. And so this is what a screenshot of the Stellarium is like. So once you install it and run it, so you can download it from this website. And then here, if you click this, for example, this is the location window. You can enter your location, and you can using by clicking this, you can enter your time, then you can search for any stars, and you can look at what your night sky will appear, different directions, you can go close and so on. Ratna will show you at the end. uh, and then what do you need to do after that? After that, of course, you enter your location, time. You need to select 25 bright stars in your night sky. So in your night sky, in Stellarium, you go and look at these stars which appear bright to you and click on each star. And when you click on each star, you get a lot of information about the star. Okay, there'll be a lot of information about its coordinates, its parallax, I mean at what rate it is moving and so on. Don't worry too much about those. You just note down spectral type and its subclass. Usually it will be given as something like A2, B5, and now you know what these mean. This is the A spectral type, this is the B spectral type, and this is the subclass. Now you will find there will be alphabets beyond this, Roman 1, Roman 2, Roman small a, small b. Ignore all of that. You just take the first two digits, or in the sense alphanumeric values, that is A2, B5, and so on. And next is absolute magnitude will also be given for these stars. So note down its absolute magnitude. As I told you, it's a proxy of the luminosity. So you make a table of these quantities. The star name, you can also note down the name of your star. You can note down its absolute magnitude, note down its spectral type. And plot the spectral type on x-axis and absolute magnitude on y-axis. So you draw a graph like this. It's okay. So on your x-axis is the spectral type in this form. And as you know, you can go from O0, O1, O2, O3, so on. In B, you can go from B0, B1, B0 will be here, by the way. B9 will be here. So please, B0 will be hottest. So B0 will be here, and B9, B1, B2, and so on till B9. Then A0, A1, A2, and so on till A9. And this way you can consider the x-axis. On the y-axis, plot the absolute magnitude. Since it's negative logarithm, you have to go in this in the opposite direction. Okay. Now, what you need to do is you make this plot and see where the stars lie. Do most of the stars lie in the band, in the main sequence band? Do you see some giants, or do you see some supergiants? Do you see, for example, some white dwarfs? Maybe, maybe not. Then you, if you're not, if you're happy with your plot, or even if you're not happy with the plot, it makes a sense to actually go and populate this much more. So you can go out and identify many more stars and start writing down their names and populate your HR diagram. And as in when you start populating, you can draw your own conclusions and see whether it is very close to what I have shown or not. From this, statistically also, you will be able to tell whether most of the stars are lying in the main sequence band. And that statistic itself will tell you that if I consider a sample of stars and most of them are in the main sequence band, that means the star spends most of its lifetime in the main sequence. Okay. So, and of course, a very nice addendum to this activity is you actually, since you have looked at the star very carefully and looked at its position in the night sky, go out and really try to locate it in your night sky. I think that will be also a very useful exercise. And when you go out, you know what its temperature is and you know what its magnitude is, what its luminosity is. So, with this additional information, now you go out and look at these stars and try to see whether the more luminous ones are, whether they appear bluer or not, and whether the low surface temperature one, not luminous, more higher surface temperature, like the O stars, whether they appear bluish, and something which is seen as reddish, whether it is lower surface temperature. Okay. Now, this is general stars. Now, are you interested in clusters? So, additional activity is you can go and within stellarium you can go and click and search for Pleiades. Then you will see a small group of stars. I'm sure many of you have seen Pleiades through binoculars. Looks beautiful actually with the binoculars. So you click in stellarium and then zoom in. Once you zoom in, you will see these stars very clearly a lot, and it will be something which is similar to what is shown in this picture. Then you go and each individual star in this cluster, this is a cluster by the way, you click, and once you click again you will get all the information, and then you can make HR diagram of clusters themselves, and then you will be able to see is there a turn off point. That may not be very easy, but it's something you can try. Okay. And because main reason, for example, in doing this activities, you may not know which belongs to Pleiades cluster and which are background stars, but nevertheless you can go and try out and see what you find. All right. So with this, thank you very much, and over to you, Ratna.
So thanks for taking us through those jewel-studded paths, Sarita. That was lovely. And there was somebody who was asking also where is UV Scooty, and perhaps
You can show
one thing.
stellarium.
Yeah, I will do that. I am trying to share Stellarium and then show some of the
Huh.
things which you
Yes.
were talking about. But
Yes.
the thing is that the version I have maybe is
Huh.
a little different. So
Huh.
when I'm actually clicking on a star, it is showing. Oh, now
Spectral
what?
type will be below. Last spectral type is
Yeah. It is showing the spectral type at the very bottom. So all right.
yes. And
So
you
that's
can
there.
show, for example, here what are only the first two, the spectral class and subclass needs to be taken, and you can also
Yes,
show
yes,
where the absolute magnitude is, and
yes.
so these are the two things that they need to take.
Yes,
Not the
this
magnitude, there is
uh,
absolute,
yes,
not
absolute
magnitude.
magnitude here and the spectral
Huh.
type at the bottom.
Yes.
And so let's try to find the star that you wanted. Yeah. So I hope my screen is visible.
Yes, yes,
Will
it's
you check,
visible.
Sarita? Hmm.
Yeah, yeah,
All
it's
right. So
visible.
what I will do is I'll just remove the ground now, and that will do for now. And so, let's remove solar system also.
Maybe you can show in the beginning, know how to enter the location and things
Actually,
also.
quite a number of the participants are
People
aware of
know.
it. We have also
Okay,
done
okay.
a few sessions of just
I
simple
see.
sky gazing with stellarium. I'll
Okay.
uh, I'll show a link of that. So, all right. So that's your UV Scooty, and so this is custom object. It says. So there was somebody wanted to
Yeah,
know about this, so I just pointing this
but I
out.
don't know.
And
See,
you were
it's not
mentioning the
shown now.
Pleiades, no?
Yeah.
So for looking at clusters, I think one thing is probably if we use the Messier catalog, it has a number of open clusters and
Yes, yes,
global. So
yes.
yes, type M and then type any number from 1 to 110. You will find beautiful objects in the sky. Almost, like it'll be an entire
M67.
astronomy
You can
lesson to
try.
understand all those different objects.
You can try
M3 I think is a
M67.
globular cluster. M3 is a
Okay.
globular cluster. So if you wanted to, but that's too crowded.
No, no, no,
So to
no.
do the kind
That's
of
a
exercise,
that's a
no, no, yeah, it
went
isn't.
to
Yeah, it's a galaxy. When I typed M3, it went to M31.
It's
I'm
M31.
having a bit of a mouse problem. Okay, now M3.
Uh-huh.
Yeah, that's a galaxy. That's what I've. So let's. Why is it not going to M3? Okay, कोई बात
मेरा
नहीं. Uh,
M67.
M3. Whenever I say M3, there it is. Yeah, there it is. Fine, fine, fine. Now we have reached the globular cluster M3. And though here at the
But
center the
yeah.
field is very, very crowded,
And
but
and the point is, you may not have spectral types given in stellarium for many objects. Faint
yes,
objects, it may not be there. That is why,
actually,
if
just
you are able to see it, those are well-studied objects. The spectral type will be marked. Okay, so that's why all spectral types of all objects may not be there in stellarium. So this is
Hmm.
something that one needs to keep in mind.
And I think M43, right? I
M67, you can try M67 for example, or
no,
Hyades.
for your object. Sorry, sorry. No, M33. No,
M67.
I forgot what is Pleiades. Pleiades, yeah.
You just type in
I didn't-
Pleiades. Type in
Yeah,
Pleiades.
yeah, 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 yeah.
Huh.
There. Here you will
Huh.
get, I guess. For each star, you may
Yes,
get.
yes,
For quite
yes,
a number of
yes.
stars, you may
Yeah, they
get
have
that.
noted down. Huh? Huh. No, you
Mhm.
go to this
For a number of.
Electra, for example. Not all, you may not get for all, but whichever you get,
Mm-hmm.
yeah, spectral type and a B6 is there.
Yes, 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 yes. So that's nice. And
Huh.
Ritvik, I hope you are listening because you have been asking. This is exactly the kind of project which you should do. I'm 45. Kritika tells us. Yeah,
You were about 43.
yeah. I don't remember these names. Thanks, Kritika. She had a question also. Now I think I should go to the questions they all had. So yes. So you are back in this the studio link, right, Sarita? Then you will be able to see the questions.
Yes, I'm able to see the questions.
But
Okay. I'm
why
seeing
is it?
infinite
Yeah,
versions of
yeah, yeah.
us.
But I don't know why it is showing in such small script. Usually it comes
No,
up
but
in
I can
larger
see,
script.
I can see
Hmm.
what are the techniques
Hmm.
which are used to estimate total number of stars in our galaxy. Okay. So this is the question that Kritika is asking. So, for
Yes.
example, the earliest ones, what they did was, like for example, Herschel and others, what they did very long ago, they actually mapped out that using that if I have a certain number of stars between, you need to have the magnitude range also. What is the range till which your eye can see, for example, or your telescope can see. Then beyond that, you have to use some models to do it, because your telescope, even if you want to measure with your telescope, you will not be able to see very, very faint stars. Okay, so you will need to make some estimates that your telescope can see up to so and so, and your magnitude range in so and the density of stars in different regions of the sky. So that much little bit of measurements you do need to do, and that is what, for example, Gaia also intends to do. Earlier with Hipparchus, they had made Hipparchus was an observing mission. They had tried to estimate how, build a model, of the galaxy, but very difficult. Sitting in our own galaxy, making a model is as difficult as tying you to a chair in a room and saying make the whole architectural design of the building. So it's very, very difficult to do these kind of measurements. But surprisingly and very interestingly, people have come up with various techniques and means, which is like looking at stars with the telescope and noting down the range of magnitudes. Then you and based on that, you scale that I'm able to see up till so and so magnitude, and knowing the distance to some of these stars, to all extent you expect it to you expect stars to be there. That is, the distance measurement is essential to make models. And so ultimately, the number of stars, as you can see, 100 billion to 400, that's a pretty big range. That's because we do not have very accurate estimates, and it is all very model dependent. That means in different directions, what is the number of stars that we see? And if you go in the night sky out, you will see that stars are distributed in the Milky Way, so the density of stars is higher there. And based on that, essentially, it is some rough star count which is extrapolated using various models and various interpretations and understanding of other galaxies, and extended to get models of to get the total number of stars. So now the Gaia mission, one of its main objective is to make look at very faint stars and go look at very far stars, so that you can see stars to the other side of the galactic center also, and make very accurate models. So you need more and more measurements.
Sorry. There is a question from Arindam Konar, which I think will help us to give the classic explanation of HR diagram snapshot.
Huh. Okay. The lifetime of a star, very interesting question, I personally think, because see, if you see, actually, we have been doing observations of astronomy observations since Galileo's time, so like put it at 400 years, and yet we are talking about main sequence lifetimes of stars, right? In fact, you can do very elementary calculation to know that the lifetime of the sun is 10 billion years, and you'll be surprised, how elementary calculation it is. It is like, if I assume, take the mass of the sun, we know the mass of the sun by whatever means, we know the mass of the sun, and we know, for example, what is the if you assume that the central, and it's assume that it's all made of hydrogen, forget helium complications and all, assume it's all made of hydrogen, and then at the very center, suppose you take the 10% of the core at the center, and you say, I want this 10% hydrogen to be converted to helium. So per reaction, I need 4 hydrogen nuclei, 4 protons to make 1 helium. So I need to calculate how many hydrogens and each of this reaction, I know how much energy is being produced. So you take the central 10% of the mass, and then how much energy is released based on this mass, I calculate. Then I divide it by the luminosity. That means how much is energy radiated by the sun every second. And that will immediately give you a lifetime, which is the main sequence lifetime. And you will be surprised that even with this simple calculation, you will end up with a number which is 10 billion years. So people do simple calculations like this, and this is about main sequence lifetime. Now about other evolutionary stages, how do we know? What we do know is that's the important thing, by looking at clusters, by looking at how the stars of the path, how the path of the stars are changing in different clusters, and they seem to be following, some are turning off at a higher mass, some are turning off at a lower mass, and then you see the other branches, and then you model it, that how things are changing. I'm not saying we are perfect, but we are good enough to be able to say that this is the effective temperature outside and luminosity. Internally, exactly whether we are modeling correctly or not, we do not know yet fully 100%. What we do know is the outer properties we are able to model to quite a bit of extent, and particularly for the sun, we are very happy in the way things have happened. I hope that answers your question.
Okay. So there is the other question. Vansh, he has been asking this about the Dyson sphere. Yeah, are you able to see that? Or hear me?
Yes, but this is something which is not related to what I talked about, so
Yeah,
I'm
yeah.
not
There are a couple of
able
questions like that. Yeah, okay. We'll maybe come to
yeah,
them toward the end.
yeah.
Even this, in a sense, I mean, but this is stellar revolution related. Whether there's going to be a naked,
Yeah.
it could be any time there could we could have a naked eye
Yeah.
supernova.
We are
Huh?
due in Milky Way. Apparently, we are due, because they say that based on observations of other galaxies, we would know it is expected that every 50 to 100 years, one supernova is expected in a galaxy like Milky Way, but we have not seen one since 300 years or so, or some time of that order. But we are due, and hopefully, we will see one in our lifetime and not too close.
uh, Shrishti had this question earlier also, and she has put it again. And yeah, astronomers
Ah.
use strange language.
Well, see, there's no reason why they are called metals. I don't know, but I think that I don't know answer to that, because many things that we is more like what do you say? It's just something that has come down over tradition. For example, this inverse scale of temperature, calling hydrogen and helium metals, and so on. So there's no specific reason why they should be called as metals. You can call them, I guess, anything else. Heavier elements is more appropriate than metals, but I can't think of any reason why we should call it metals, because the way we define metals in normal physics, they need to have certain properties. Obviously, they don't go in that category.
Kritika was asking, does every star has its own planetary system?
Yes, this is a very, very interesting question, particularly now, because lots and lots of exoplanets are being discovered, planets around other stars. And people are also very curious for the obvious reason, because we want to know if there's other life, whether it's as intelligent as us or less intelligent than us, that's a different thing, but whether there's life. So in that process, they are trying to look for other planetary systems, and they have found, in fact, very interesting planetary system. In fact, and they do it by indirect means, numerous techniques, because planets are very faint. But people have imaged some planetary systems or protoplanets, and some planets they have imaged, and then through various new indirect techniques they have found many planetary systems. But you can't do these measurements to far off stars. You can only do to close by ones, because you need to have very sensitive measurements to be able to say if there's a planet or not. So the closer by stars, particularly the cooler stars like the KM stars, people have been trying to look. In fact, there are missions like Korot mission, Kepler mission, which are particularly aiming at looking for exoplanets. But whether it is near all stars, I don't know. The question is whether hot stars, a planetary system, will even survive. We don't know.
Hmm. Actually, our sun, we are not in any binary system or in a cluster or anything, but we do still, I mean, kind of estimate that perhaps most stars are in binaries and most stars are in clusters
Yes.
and so on. So we are a one-off in so many ways.
Kind of. Many stars are in binary, but there are also many field stars. Field stars are stars which are not believed to be. So they are stars because over time, if you see a cluster, how it evolves. I have not talked about the morphological evolution. So over time, these stars are also expected to slowly dissipate out. Was there any break, or it's okay?
No, no, no. My mouse is having some
Okay.
problems. So that's all.
Okay. So over time, these stars, because of they are continuously interacting with each other in the cluster. They are gravitationally bound. They are interacting with the cloud and so on. Over time, these stars are kind of expected to slowly have high velocity interact and maybe leave the system entirely. That's called, particularly you see a lot of stars being lost from globular clusters. In our terminology, it's called evaporation because it's lost from the system. So stars do get lost from the cluster, and then it becomes a kind of free floating object. And those stars become what is known as the field stars. But we, for example, we are 4.5 billion years, and we are very unlikely to have been part of any globular system. We are very much in the plane of the disk. So we may are believed to have been a part of an open cluster, and then over time, maybe people are trying to look for its origin, maybe a companion. We don't know. I mean, it's people are trying to do these studies, but again, it's like you are bound to a room and then you have to find out, look everything around you and try to figure out.
Okay. Vansh has been very interested in the Laniakea supercluster. He's asking us to show it also, but I don't think Stellarium would show it.
That
Uh,
is this supercluster that he's talking about. I think he's talking about a galaxy cluster. Whereas I'm talking about
yes, you're talking of
star
stellar
cluster.
clusters. Yeah,
Yes,
yeah.
yes.
Yeah, maybe it'll be good to differentiate the two just so that
Yes,
for
yes.
him,
So,
he will also.
yeah. So stars are found in groups called clusters, and then a big aggregate of these stars is something known as galaxy, and all of you are familiar with elliptical galaxies, spiral galaxies. Then on larger scales, it is found that even these galaxies are grouped together, which is known as a galaxy cluster. Okay, so then there's a local group of which the Milky Way is a part. Then you have supercluster, because again these galaxy clusters are found to be, this is okay, going into cosmology and going looking at very very large scales and finding that there are even clusters of galaxies are grouped together into much larger aggregate called the superclusters of galaxies. Okay, but what I am talking about are very small. I mean, compared to those kind of big scales, these are very small scale objects, and these are just stars, groups of stars
Mhm.
known as star clusters.
Uh, Ashirwa Tillu wants to know her big hero, though I
Okay.
wants to know
I
about
can
this.
I can talk a little bit, yeah. So as I told you during the stellar formation phase, I told you that you have these objects called jets, which are coming out from the rotation axis. Matter is given off from this very very young star, and it is coming out in the form of a jet, which is in the direction of rotation axis. So what is this jet? Basically, it is ionized particles. Okay, high velocity ionized particle. So as this ionized particle goes and hits the ambient interstellar medium, there is the gas gets shocked there. Okay, that means there are drastic change of conditions, that's called shocks. Drastic change of conditions of temperature, pressure, and so on. And you see, because of this particle hitting this dense interstellar medium and the shocked gas, you will see that it in these regions these regions give off radiation. They become bright nebulous objects called as Herbig Haro objects. Okay, so this shocked gas from the jets from young stars are known as Herbig Haro objects.
So the time taken to travel across the galaxy.
Yeah, across the universe. So I don't even know
Oh,
the
oh,
end of the
universe.
universe.
No, let's take it as the galaxy itself, because that itself is of interest for the sun
Yeah,
to
so
go
one
around
can do
the
is,
galaxy and all that.
yeah, but if you, yeah, so the sun, for example, we'll not talk about universe, let's stick to the galaxy because the
The
extent of the
galaxy.
universe we do not know. So the galaxy, for example, sun is, okay, so let me tell you, the extent of the galaxy you can think of, you all know parsec, right? Or should I talk in terms of light years? So light year and parsec, there's a factor of 3. So a sun is like approximately 25 kilo light years from the galactic center, and 3 times of that. And the radius of our galaxy is, you can take 3 times of that, which means around 75 to 80 kilo light years. Now, even if you consider the radius of the sun, which is like 24, 25, approximately 25 kilo light years, and the speed with which the sun is moving around so the galaxy, because now you know the Milky Way is a galaxy which has a kind of disk structure. The moment you say disk structure, that means it is rotating. There is a rotation effect. So sun is also actually moving. All the objects are moving around the galactic center. So the sun, for example, it is moving at a speed of 220 kilometers per second. So now you do this calculation, you know the radius, you know the speed, you can calculate how much time it takes to make one galactic revolution. And what you can next do is, you know the age of the sun now, which is 4.5 billion years, and you can calculate how many revolutions sun has made around the galactic center. So these are elementary calculations. I urge all of you to do it.
Yes, I was suggesting to him in the chat also to make this kind of an estimate. He was also asking about quantum tunneling and so on, but that is again not on topic. And he
No,
wanted to know whether it
quantum
is in real
tunneling,
world.
maybe.
You have to be a quantum
No, quantum
domain for
tunneling, I
it to
can
be.
comment little bit
His
in
question
terms of quantum tunneling, because in the sun, for example, when you talk about
was
nuclear
that
fusion,
at those quantum levels.
if you in quantum tunneling, I can talk a little bit. What we can do is, for example, if you know about um, if you want to calculate, for example, what is the temperature that is required for protons to undergo fusion, because the first step of this fusion, to from
Hmm.
hydrogen to helium, you want to fuse four
And
protons. It goes through a sequence of steps, and the first step involves fusion of two protons to deuterium, but that is a very difficult process because this electrostatic repulsion. So you can calculate how much is the energy required for these two protons to come close together to one Fermi distance, and how much is the energy required, that you can convert to temperature using KT formulation. And you can calculate the temperature which is required for fusion to occur. And with the simple elementary calculation also, you will find temperature of 10 billion Kelvin. But in the center of the sun, we never achieve those high temperatures. The temperature at the center of the sun is of the order of 15 million Kelvin. So how is it that fusion is occurring even if it is 15 million Kelvin, whereas you need temperatures of 15 billion Kelvin? So there we estimate that this is happening because to cross this barrier, the tunneling happens. So there is tunneling happening, and because of the tunneling effect, even at lower temperature, we are able to have a fusion in the center of the sun. So I hope
lovely.
some
Yeah.
example of tunneling I've given to him.
Okay. Now Suchayan Mukherjee wants to know
What
about
is
seafood variables. I think it will be nice to talk about seafood variables just a little bit.
Yeah, so Cepheid variables are again in the later evolutionary stages of the star. And in this later evolutionary stages, these are stars which are unstable. I mean, they undergo dynamic instabilities in the outer layers. So, because see, if you look at the case of the sun, in the main sequence phase, things are not changing, it is constant. So, most of the stars will remain, will shine with the same light, you will not see any change in properties. But there are some kind of stars like Cepheid variables or RR Lyrae variable stars. These variable stars show periodic variations because of various processes. I won't go into those details, but they are continuously kind of pulsating stars. So these, because of these pulsations, their luminosity also changes periodically. And we know enough to know that the change in the periodic luminosity is very precise. And the higher luminosity ones will have periods which are higher in time, and the shorter ones will have shorter. So they have, there is a famous period luminosity relation, right? So the Cepheid variables, because of this dynamic instabilities in the outer layers, they undergo these pulsations because of which the luminosities are changing. And these are also used for the distance ladder estimation. I mean, in the distance ladder.
I think most of the questions have been handled, but if some have somehow missed them, please type them again very quickly. And Vansh had another question too. He wanted to know whether a star can change into a planet. I mentioned to him that low mass stars could become white dwarfs, and
Yeah, but
but
no, they can, because planets are very low mass. Okay, and a star cannot become a planet. Planet is really, really low mass compared to the star. Okay, so there's no way that it can become a planet, and planet does not have any fusion in the center, right? So you can't have transition. You can't even have transition from O type star to B type star or so on during the main sequence phase. It's very unlikely that you will have one star turning to another type of main sequence star. But the evolution which I showed, that is the best evolutionary path according to our understanding. And we see that happening even in clusters, the way things move.
okay. So thanks for so patiently answering all the questions, and all of you for asking so many interesting questions. If there are there. Yes, I think. Yes. Shrishti has a question still. It's okay, no? Maybe
Yeah,
just one
no
or two
case, no
only.
problem. I'm happy to
Hmm.
answer as many questions as possible.
She wants to know CFED are variable types of pulsars or
No,
neutrons. No,
no,
no, no, no. They are
they
not.
are another class.
They are another. They're more. I mean, they're stars. Pulsars and neutron stars are end
Okay.
states.
So where can we locate them in the HR diagram? Okay, so you can locate them. Usually these kind of stars, it's easier to find them in globular clusters. So in globular cluster, I had shown this diagram, right? You had these giants. Can I go back and show, for example?
Yeah, if you will go to your
Yeah, I'll do it.
presentation page, then I will add it into the.
Okay, but I came to this, exit full screen. Hold on. Yeah.
Yes.
So,
Yeah, I've added it now. It's visible.
yeah, yeah. So I can show you the RR line. So here, if you see the globular cluster, what we see is this is the main sequence phase. This is the turn off. This is the giants, subgiants. This is red giants. This is the tip. Then you have something called a horizontal branch. Okay, and in this horizontal branch, you will see a gap here. The gap you will see here because these stars are continuously varying. These are the RR. This is called the RR Lyrae gap. Okay, Cepheid variables are up here. Okay, so they also will show as a gap because you cannot attribute a constant luminosity to them because they are varying in their luminosity. That's why in HR diagram we show them as a gap because their luminosities are changing, right? They are variable stars. That's why they are shown as a gap. Okay, but this is their location, and the Cepheid variables are expected. So there is, in fact, people have estimated that there is a region of instability here because of the processes and so on, which gives rise to this kind of dynamic instability. Okay. Okay, Ratna, that's about all. I
I
think
think,
we'll stop
yeah,
this.
yeah. Yes, yes. I think we would. So that was lovely. I mean, going through uh, so many of what you had shown examples of the hmm, stars located at different parts of the HR diagram. For somebody who was asking about in the, I mean, in over generations is what whether we can get idea about the HR diagram, so on. So that aspect of HR diagram, that it is that snapshot that although we cannot go through all the stars, but then there are stars at different
Yeah,
lifetime, different stages
yes,
of
in the
lifetime.
different
That's so
clusters.
thrilling
Exactly.
aspect
Yes.
of it. So now there is a WhatsApp group, and somebody was mentioning about that. So what I will do is I'll put it as the WhatsApp group link I will put in here. So I can't exit the. All right. I'm having a little bit of a problem. Sukhvinder Kaur, just in case I'm not able to give you the link, can you also post your number or an email address or something so that I can send you the WhatsApp group link? I will try and put it here, but it's going to take me just a few minutes. I hope even after we end the broadcast, I'm able to give you the link to that. Or Sarita, if you don't mind, just I will
No,
type
I'm
it.
fine. I'm fine.
Huh?
Yeah, please go ahead.
Because some of the participants may want to come and join into this WhatsApp group. Unfortunately, it is not opening on my system. All right, any of you who want to join, there is a WhatsApp group. Many of the participants are in it. There are actually two of them. Please send a mail to Nehru Planetarium at Gmail if you don't get it as a link on this. All right, then you can join in. So, Sukhvinder, please send a mail to Nehru Planetarium Gmail. Hmm? I'll give you the link. We are going to end the broadcast here now. Thank you. That was wonderful, Sarita. It was kind of, such a lovely journey through this um,
Thank you.
class. And I am ending the broadcast now.